Okay, good morning everybody and welcome to the video on inclined planes for the college prep class. Inclined planes are simply a tilted flat thing. Inclined is tilted, flat thing is a plane. So let's first talk about what happens when you set a normal object on a normally flat plane. And so we're going to put a box, something that's fairly heavy. Let's make it 5 kilograms, right on a flat plane. So a free body diagram for this situation is pretty boring. There's going to be some weight to this thing, Fg, and there's going to be a normal force because it's sitting on a plane, Fn. Fg is m times g, and that's going to be somewhere in the neighborhood of 50 newtons because g is about 10. That means this is also going to be 50 newtons. So far, so good. But what if we tilt the plane? What's going to happen? Well, I'll go right here and I'll draw a reference line. It's the same old flat plane, but now we're going to tilt part of it. That looks like a pretty serious angle, like about a 30-degree angle. And now we're going to put the box on this tilted plane. I haven't said anything about friction, and so let's just ignore friction right now. Let's pretend there is no friction. Let's draw a free body diagram for that situation. Well, it's going to be a little different. The weight component is going to be the same. It's going to be downwards, and it's going to be about 50 newtons. But the normal force is now going to be perpendicular to the plane, which is at this angle. It's been tilted over here. It's 30 degrees away from where it used to be. Now, when I look at this diagram as a practicing physicist, I can immediately conclude there's no way this object is going to hold still. For equilibrium, we need equal and opposite forces, and these aren't opposite. So even if they were equal, the box would still move. And just looking at the situation and imagining there being no friction, this is a Teflon-coated metal ramp, this box is going to go this way. It's going to slide that way. So that kind of gives me a hint to a couple of things that are going on here. Okay, now going back to the free body diagram, anytime you have forces that are not in our coordinate directions, we normally componentize. We normally break things into components. But I'm here to tell you that there is a secret to making this problem easier, and that is to tilt the coordinate system. That will make your life easy. So let's do it. Let's tilt the coordinate system. I'll make another copy of this free body diagram right here. Let's tilt the coordinate system so that the x direction, instead of being horizontal, is parallel to the ramp. We're going to tilt the thing by 30 degrees, which would mean that the y direction, which used to be vertical, is now going to be perpendicular to the ramp. And then you could see in this tilted coordinate system, in fact, you could even just turn the diagram so the coordinate system was back to normal if it offended you. But in this tilted coordinate system, it's the weight that needs to be componentized. Now, this is the part that's a little difficult. How do you break this weight into its components? Well, one of the components is going to be down the ramp, and the other component is going to be perpendicular to the ramp, but into the ramp. And this 30-degree angle actually shows up right here. That's the part that's really interesting. Now, you're going to have to figure out for yourself why that is. I like to think of it, well, let's do a couple drawings. Let's go over here to this blank area that I haven't used yet, and let's talk about why that is. First, let's draw a flat ramp, then we'll draw one that's slightly tilted, then one that's very tilted, and then one that's just crazily tilted, okay? So this is 0 degrees, maybe 10 degrees, maybe 40 degrees, and maybe something like 70 degrees. So let's see what happens to our coordinate system. Well, this one is flat, so x is still horizontal and y is vertical. This one is tilted a little bit, so x now tilts up a little bit and y tilts over a little bit. And this one is tilted even more, so x tilts up and y tilts over. And in each of these cases, the direction that is straight down towards the center of the Earth remains the same. So you can see that as we increase the angle of the tilt, this negative y-axis moves away from the direction of weight. And in this case right down here, it is the worst of all. the negative y-axis has moved 70 degrees away from the direction of weight. So it's 70 degrees in here. So that's why this angle is right there. And now once you know that, then you can say that these two pieces, this one is going to be weight times the cosine of the angle, and this one over here is going to be weight times the sine of the angle. It's easier to see that if you draw this vector down here and use it to finish off the triangle, then it's clearly the opposite side of a triangle. So once we've componentized, we can redraw the free body diagram, and on this new free body diagram, we're only going to have components. So there's the normal force, there's weight times the cosine of the angle, and there's weight times the sine of the angle. And now with this new coordinate system, in fact, let me put the axes back on. Okay, with this new free body diagram, it's really easy to see what's going to happen. These two forces here are going to balance each other out, and the box is not going to accelerate perpendicular to the ramp. But this force here is going to produce the acceleration, the sliding of this box down the ramp. So here's what I think you should do. I think you should simply memorize that the force that is parallel to the plane is equal to the weight of the box times the sine of the angle. And the force that is perpendicular to the plane, or at least the part that is from gravity, is the weight times the cosine of the angle, and that's also going to be equal to the normal force. Those two are going to be equal. So if you memorize this, you will get through inclined plane problems. Now I'm asking you to memorize it, and I'm not normally a memorizing kind of guy, but inclined planes are considered very difficult by first-year physics students. And I know myself, I got the sine and cosine backwards for most of a year. It cost me a lot of points on a midterm at UCI because I reversed those two. And I wish somebody would have told me just to memorize it this way. Unfortunately, I was stuck in the world where cosine was for x and sine was for y because that's what my trigonometry teacher taught me. But it's not. It's reversed in this case. This parallel direction, parallel to the plane, is the old x-axis, and it's using sine. And this perpendicular to the plane is the old y-axis, and it's using cosine. All right, so that's a good way to start inclined planes. We'll do a little more with that when we do some examples, and I hope that sorts things out. I have another video that's available on my YouTube channel that's designed for the AP classes using a slightly different notation, but it's the same information, and almost all of the major physics help areas, they have these inclined plane videos.